Okay, hello everyone. So we're going to start looking at cache memory, right? We're going to start looking at cache memory, right? This is in architecture. So first thing we're going to do is that we're just going to make a few things, more like define a few terms that we're going to be using, right? If you've gone through your notes, most of these should not be exactly new. But let's imagine this is our RAM, right? This is our RAM chip. Then I'm going to separate it into segments, like so. Something like this. Yeah. So say this is our RAM, right? And then now we have our cache memory here, right? Now, cache is basically just a way in which we store data intermediately before it goes off into our CPU, right, for faster access. Now, there are a few things to note here. First of all, in memory of memory locations, right? We have these memory locations. We have memory locations. So let's imagine these over here are memory locations, right? So we'll have memory locations, and then those memory locations are further grouped into something called weights. Oh, sorry, blocks. Right. So let's say 1, 2, 3. It's usually in powers of 2. So let's say we have a block. So we have memory addresses, and then we have memory addresses, and the data they store in here is called a word, right? So they store a word, and then those words are then grouped in powers of 2 into something called blocks. Then now, if we go to our cache memory, we also have lines in here, right? We have these things that we call lines, and then each of these lines can store a block, right? So if we say this one line here can store this entire block, right? So these are just a few things that we're going to keep track. This is just a few things that we need to take note of, right? And then now we have different cache mapping algorithms, right? These are ways in which we map our cache. The first is direct mapping. And what direct mapping basically is saying we have all these blocks, right? So let's say we have 50 blocks in memory, and then we have 5 lines, right? We have 5 lines. Now, if we try to get, let's say, from line 0 up to 4, those will fit in line 0 up to 4 as well, right? But then now, if we start looking at other blocks, let's say 5 to 9, 10 to 14, right? We have these. How can they sit in there? Well, we put them in our cache in a more of a round robin manner. Now I'll explain what most of this stuff means as we start solving questions. But basically, what it means that we know where each block will stay, right? So there are calculations that we're going to do, but we always know to say if we have, let's say, block. I can say, for instance, block 5. We know that block 5 will always sit in line number 0. If we have block 0, you know this will always sit in line number 0. If we have block 10, this will always sit in line number 0, right? If we have, let's say, block 4, we know this will always sit in line 5. Block number 9, that will always sit in line 5, etc., etc. So this is direct mapping, right? We know that for each block that we have, it will always sit in a specific line in our cache. Now, since this cache, of course, it already has data at some point. If we, let's say, loaded in block number 5 and then we load in block number 0, of course we would have to replace the data that's in here, and we'll of course talk about different replacement algorithms and how we replace the data in that cache, etc., etc. But then moving on from direct mapping, uh, again, most of the stuff will become clear as we solve. We have something called associative mapping. Associative mapping, you can say spell associative mapping, but basically what that means is that we don't care where we put the block, right? As no matter how many lines we have in our cache memory, what we don't care about any of that. What we do is we say if we have a block, just put it wherever there is space in our cache, right? If we have a block, put it wherever there is space. This is why now some replacement algorithms that we'll talk about later on, where they come in handy, and I'll explain them as we encounter them in questions, of course. Then we have set associative. What set associative mapping is basically to say, okay, we have direct mapping where we always assign a specific block will always sit in a specific line in cache memory, and then we have associative mapping where we don't care where we put it. So what if we had a situation where we demarcate our cache into something called sets? So let's say this is our cache memory, right? And then this cache memory is split into sets. So these sets will of course have lines, right? These sets will of course have lines in there, right? These sets will have their lines. And then what we say in set associative to say, okay, if we have sets 0, 1, and 2, when choosing these sets, we more like use a direct mapping approach where we say, we always know that block, let's say 0, always sit in this set, right? Always not block 0, always sit in this set. Always not block 10, always sit in this set. Block 22, always sit in this set, right? But then now, the only thing we determine is the set it sits in, but not the line, right? We don't necessarily determine the line that that block will sit in. So, set associative mapping is more like a combination of the two. So we know exactly which set will always put that block in, but we don't care about the line that it will sit in, right? Our replacement algorithms will handle how we're going to replace that stuff, as we'll discuss them later on, right? So with this covered, then now we're going to just look at a few more things. First of all, back to our direct mapping. Direct mapping, you usually hear something called a physical address, right? A physical address. And what that physical address is the address of each of these memory locations. So each of these memory locations in memory, they have an address. So this is address 0, address 1, address 2, address 3, address 4. Now, when we look at it from direct mapping, from that direct mapping point of view, if we have, let's say this is our physical address, right? So our physical address. Now, there are a few things that we need to take note of. First of all, this physical address is viewed in two perspectives. First of all, there's this perspective of saying we're getting it from this point in memory, and then there's this perspective of saying this is how it sits in cache. So remember, I said in direct mapping, we are able to determine to say it will always sit in this block. How do we do that? Well, this address is split into 3. Right? So we have the first bits here, the first few bits here, which we call W, here, and what these bits are, these guys are used to determine where it sits in the block. So remember, the block, let's say it's storing 4, right? We have a block size of 4, meaning this one has 4 words there, meaning it has 4 memory addresses in it, right? So what this is used to demarcate is which word, right? Which word are we referring to? Right. So for in our instance where we have, let's say the block size is 4, so we're going to have 2 bits, 0 0 0 1 1 0 1 1. So meaning this, we can say, okay, this is the first word, second word, third word, fourth word, right? This is what we can have here. So these bits here are used to determine what word we're using. Then these ones are called the line bits, right? Line. And what is again they're used to show is, okay, what line are we currently focusing on, right? This is what this means. What line are we currently focusing on? And then this determine the tag. So the line here basically just says which line will we put this guy in, right? Which line will we put this guy in? And then these tags are used to show which part of memory we're from, because remember, multiple blocks can lay claim to a memory a line in our cache, right? So we need to identify to say where has this block come from, right? So it's what the tag is used for. So I'm basically saying, okay, you came from the first part of memory, this one came from the nth part of memory, the j part of memory, etc., etc. So that's what the tag is used for. Then now, other things to note is a combination of these bits here, right? These bits here determine the number of blocks, right? These determine the number of blocks that we have, right? These bits determine the number of blocks, and then these bits over here determine our cache size, right? And all this is in powers of 2, of course. So mean our memory address would be 2 to the power n being the number of bits that we have in our address. Then our number of blocks would be 2 to the power s, right? Our block size would be 2 to the power w, because that's the size of blocks here. Then our number of lines, right? So we have our lines there. This would be 2 to the power, if I'm not mistaken, we use r for that. Then now for our cache size, we say that is 2 to the power r plus w. Then our number of blocks, we've already said it's 2s, which is just 2 to the power t plus w there. Again, as we start doing our calculations, we'll look at how to use these better, right? So with direct mapping covered, then now we're going to look at how the address is demarcated in associative mapping, right? In associative. Now in associative mapping, again the spelling there, in associative mapping, what is that? We have our physical address, but the only thing we care about is the word, right? The only thing we care about in this case is the word, and of course the tag, right? Those are we only care about those few things. We only care about the word that we're using, and then the tag. Other things we don't care about them. So we don't care about the line it will sit in, etc., etc. So meaning, in this one, first of all, our address length, this will be our S plus W, right? The number of blocks that we have, and of course, so it determines the blocks. Then the address is, we talked about the address there. The number, the block size, or the line size is, of course, just W itself. And then the number of blocks is S, right? Again, we'll continue looking at that better. And then cache size, we don't care about cache size in set-associative mapping because again we don't care where it's going. So cache size is not something we care about when we're talking about set-associative mapping. What else do we look at? The next thing is set-associative. Right? Next thing we're going to talk about is set-associative mapping. What our set-associative mapping is basically it's very similar to direct mapping and the like. Only that, remember, I said in this one we don't necessarily care where we're putting certain things. So if we have this, so we're going to have our tag there, then we're going to have our word, and then there we're just going to have our set. Right? We're going to have our set. So a few things that we take note of is that, remember, each set can store k lines. So we have a certain variable called k, and this is the number of lines in a set. And here are a few things to note. If let's say our entire cache has n lines, right? If our entire cache has n lines, if k is equal to 1, then our memory is the same as direct mapping. And then if k is equal to n, right? So each set contains n lines, right? Meaning we only have one set. Then our cache is associatively mapped, right? Because remember, we don't care about what we put in those lines, right? We don't care about all we know is that this item will go into this set, but we don't care about the line where we put it in. So I mean, if we only have one line in that set, meaning there can only be one word at a time, right? There can only be one block at a time in that entire set. It's the same as direct mapping. And then if we look at it from associative mapping, if we have n number of lines, right? If our entire cache is a set, meaning we don't care where we put any block data that comes in. Hence, it's associatively mapped. And a few things to note here is first of all, our line size stays 2 to the power w, right? The power w. Our number of blocks is of course 2 to the power s, right? 2 to the power s, which is just this one over here. So the number of blocks does stay maintained. Then now we have our sets, right? Our number of sets. So lines of sets, we've already talked about that. We have our number of sets, and then lines. So our number of sets usually would be given this one, but our sets is equal to v, unless I'm mistaken, we're given this one, which is 2 to the power d. So say you have 5 sets, however number of sets you have in your thing. Then the number of lines is k times 2 to the power d. So remember, let's say we have 4 sets. We have 4 sets, and then we say, okay, each of those sets has, let's say, 8 lines, right? So I mean the total number of lines that we have in our item there is 8 times 4, right? This is the total number of lines that we have in our memory. Then our cache size, this is equal to the number of lines per set times 2 to the power d plus w, right? So we're going to get the block size, and we can even just try this. We say, okay, first of all, what's the size of each set, in short, right? What's the size of each set? First of all, we're going to say, okay, well, this many number of sets times 2 to the power w times k. Basically, in fact, this is the size of each set. This is the size of a single set, because you know that, okay, each line will be 2 to the power w. That will be the size of each line times the number of lines that we have, and then if we come and multiply that by the number of sets that we have the size of our entire cache. So Of course, as we solve these things will become even more and more clear. But for now, we're going to end here with the brief introduction, and then I'm going to show you how to solve questions.